Good. So now you can see it. So the thing that we arrived at now, and which is actually the final part of the model formulation business, is that y is distributed according to a multivariate Gaussian with expectation parameter x beta and covariance matrix sigma square I n. And this is now the formulation of the GLM that we will base the rest of the course on. So that's the GLM, that of course in some way is fairly abstract. Actually, in the script you will also find a lot of times that I write it as this, so that the probability distribution of y is given by a multivariate Gaussian with, of course, the same thing. I think I currently tend to go a little bit away from this notation, although it's not wrong or something. But this is this kind of notation is very helpful if you're dealing with Bayesian models, and because we're not doing that in the frequentist sense, I think I will mainly use this thing here, so this, the upper one, for the when I present it, but it's completely equivalent. That's the same thing. So this says it's a random variable which is distributed according to a multivariate Gaussian. The other thing says that the probability density function of y is a multivariate Gaussian. So that's just a very small thing. But before we now work with that, I think I actually want to make really clear what that means and how you can look at it. So I want to show you two sampling examples. So that's now sampling the GLM, and of course one can only sample the GLM if one defines the parameters and everything that is going on there. So if you think about implementing this on a computer, if you don't have a definition of x and beta and sigma square, at least in standard imperative programming, will be quite hard to sample that. So I want to look at two cases, and let's now look at two special cases. And let's look at a first special case. So whenever you want to sample the GLM, be it on a computer or in your head, you need to define all the things that need to be defined, right? So one thing that needs to be defined is the dimensionality of everything. So because you know that y is n-dimensional and x is n times p dimensional, and beta is p dimensional, and sigma square is a value larger than 0. So if you want to sample things, and you of course want to sample y, so you want to evaluate the left hand of the statements that y is distributed according to this normal distribution, you need to define everything that you have on the right hand side. And the first thing to define, of course, is the dimensionality of y. So let's say n is defined as 5. What this means in terms of data is that, of course, we use the y to model individual data points. So we are saying the data that we want to model consists of 5 numbers. But again, we are at present not really dealing with observations. We're just trying to sample our model. So we have now defined that n is 5. That's good. The next thing to define are x and beta, and these two things you always have to define together, because if you define x with a certain p, then of course the same thing applies for the beta parameter. So you cannot define like a 4-column design matrix and a single or a scalar beta parameter. That does not work from the logic of the model. So what I now want to define is x as a column of ones, and of course it needs to be 5 ones, one below the other. because our n is 5, so it needs to be exactly 5 times, in this case, one-dimensional. So that I just say it's one-dimensional, I just make this up. So you can, and we will see many different cases, but I want to focus on this case now, which also means that our beta is just a scalar value, which we can just now state, so we know that. But if we don't define actually a concrete value for beta, then of course we cannot sample that, because we cannot in a computer, and also not in your head, you cannot multiply. Of course you can, but that's then mathematical. Then you would have beta, and then you of course then that's more abstract, so we want to really make it numerically concrete. So we define beta actually as 0, and we define sigma square as 1. And now we have defined everything that we need to define. This is actually one-dimensional, so we also know that our P is 1 in this case. And now we want to actually do the sampling again. And what this then says is that we need to evaluate the expectation parameter and the covariance matrix of Y. So let's call these entities mu Y. That's now the expectation parameter for Y, which of course is given by X times B, as we see up there, which means in this case 1, 2, 3, 4, 5 times 0. And this yields what? 0, but what do you mean by 0? Yeah, so it's a 0 vector. And for the covariance matrix of Y, we of course have 1 times I5, which is doesn't really, well, we don't have to write it down. I mean, you know what it is. It's just the identity matrix with all ones on the diagonal. So now you have specified these the stuff on the right hand side, so the parameters. And now the question is to again think about what this partitioning of the covariance matrix actually meant. So do you remember what we discussed it, I think, in general, then specifically for the error terms, but do you remember also, more in general, if the covariance matrix is spherical, what does that mean in terms of the question is so complicated that I just tell you the answer to not make things too complicated. So the thing is, a spherical covariance matrix means that the components of this multivariate random entity are independently and identically distributed. So that was the stuff that we saw last time, where actually the density was given by the product of these I. And then we came up with the spherical covariance matrix. Of course, we can also start from the spherical covariance matrix and now think what this means in terms of the marginal distributions. So the distributions of the individual components. And it works as follows. So the yi from everything that we've seen is now distributed according to a univariate Gaussian over yi with expectation parameter given by the ith entry of the expectation parameter vector of the multivariate thing. So the ith entry is 0, of course, and in this case, and the variance of the individual component is given by the ith entry of the covariance matrix, and this is always 1. So the distribution of each of these yi in our 5-dimensional vector is given by a univariate Gaussian with expectation 0 and variance 1. Because we defined the variance to this variance parameter to be 1, and because we defined the beta parameter as 0. So if we now want to sample that, we can of course do that based on that logic, or by knowing that already having incorporated in our head that this is essentially the logic of the GLM, the logic of multivariate Gaussians. So if we now sample from it, and I do that for you, we have to, for each of the components, sample from a univariate Gaussian centered on 0 with variance 1. So one sample, for example, could be 0.15 minus 0.02, 0.15 again, by chance, minus 0.12, and we need another value 0.5, which is a little bit of an outlier, but not much. So what I demonstrated with this here is of course not something specifically fancy. I just showed you how you can write sampling n times, and in this case 5 times, how you can write sampling 5 times from univariate Gaussians with expectation 0 and 1, how you can write this in terms of the GLM. Yeah. So if you want to, of course, you are very familiar with that, and I think you learned it in undergraduate statistics as well, that you have a univariate Gaussian, which is actually the standard normal distribution here, NYI, with 0 and 1, and that you can draw samples from that. And this case, which you might have called the population in undergrad statistics. So there always was this population that you drew samples from. This you can write in terms of the GLM if you define and centered on 0. If you define you have multiple possibilities actually, so I did it by multiplying 1 times 0 all the time. You could of course also define all of these values, all of the ones, as whatever you like, and multiply them by 0, or you could define all of the values by zeros and multiply with whatever you like. So there are multiple, so it's not unique how you can write this as a GLM, but you can write it as a GLM. Yeah. And we will actually need this because this is a model that's behind. This is the GLM behind the logic of one-sample t-tests. So we will come back to this special case, but only when we talk actually about t-tests. So the other example is the example that we discussed previously, but I want to do that again because we now have the whole story. Namely simple linear regression. And again, in this case, let's say our n is again 5 data points, and we have our design matrix, which of course has a column of 1s, 5 under Zahl, and in the second column we have the values of our independent variable, and I define those because these are things that you, of course, when you measure something, define yourself. In this case, it's 1, 2, 3, 4, 5. Could be different values, of course. Then, if we want to sample, we have to define our beta parameter vector, and I define this in this case as 1, 1, and we have to define our sigma square parameter, which I define again as 1. And now we want to sample y as a multivariate variable from this case. So we again need to specify the expectation parameter of y and the covariance of y, which is of course, again, this is fairly easy in this case. This is just 1 times I5. So we know what that is. Mu I we have to work a little bit more for, so we have to again do our matrix product x times beta, but I assume that you all know how to do that by now. So if you do that, you get mu y equals 1 times 1 plus 1 times 1, so you get 2. 1 plus 2 is 3, 1 plus 3 is 4, 1 plus 4 is 5, and 1 plus 5 is 6. So you get this as the expectation parameter. And now you can again view sampling the individual components by sampling as we just discussed. So mu I is univariate normal with yi with variance 1. The important difference now is that to this case is that the expectation is not always the same, but as you see here, the components of mu y depend on the index. So one could write something like mu yi, which means if we want to sample mu 1, we need to sample from from the univariate Gaussian with expectation parameter what? What's the expectation parameter of of y1? It's written on the board. Mu y1, that's true, but what is mu y1? 2, exactly. Because that's mu y1 is this value, so that's the first entry in mu y. So we have 2, 1, y2. What's the expectation parameter? 3, y3. Expectation parameter 4, and so on. I'm just doing the rest now. And if we think about drawing a realization here, okay, so this is a univariate Gaussian centered on 2 with some variability, so we will likely get a value somewhere around 2. So let's say we sample 2.2. This is a Gaussian centered at 3, so let's sample something there. So let's say we get, let's take something representative, so we get 2.9. And then here we might get something like 4.1, here we get something like 5.2, and here we get something like 6.6, again a bit of an outlier. So that's now our sample, so that's now our y that we got. And finally, I want to visualize that again because this helps. Here we have 0, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So these are our entries in the second column of x. Yeah. So that's if you want, this is x1, 2, x2, 2, x3, 2, x4, 2, and x5, 2. So these are these entries. And on the y-axis, we have our yi, so that's yi, and we can plot two things actually. So we can plot mu I, so these values 2, 3, 4, 5, 6, as a function of x, so of these values, as a function of the independent variable. And let's plot those first. So for 1 we have 2, so, and then it just goes up. So we have this one, this one, this one, this one, and this one. And we, although there's nothing happening in between these dots, we might as well put a little line through that. So that's mu I, that's a visualization of mu I, of the expectation parameter. Now, of course, we can in addition plot our sample that we obtained. So that was actually 2.2 for x1, 2 being 1. So we get something here. Or maybe let's make that red. It's cooler. I want to do it in red now. It's so cool. So that's our first data point. For 2 we got 2.9, so we are somewhere here. For 3, sorry, 2.9. Am I wrong somewhere? Oh, we have a. Did I do something wrong? No, good. For 3 we have 4.1, so we have something here. For 4 we have 5.2, and for 5 we have 6.6. Yeah? So these are our y values now, and there's not much sense of actually connecting them. So what you should, so this is how to visualize just the model formulation. Yeah, so we have not acquired any data, and we also have not fitted a line somewhere. Yeah, what we just visualize is the expectation parameter of the model and a specific realization that we obtained. So maybe we call this y1. And so this is now our y1, and based on exactly the same logic, of course, we can sample again. Let's sample again, and I'm just doing that visually. So of course we will sample something around 2 here again. So maybe we sample this. Oops. And in this case we sampled something around here. Here we sample a big outlier. Here we sample not an outlier. And here we sample almost the same value as here. So based on this logic, actually today the sun is really showing into my face. Can you, oh wait, I can do it. No. Oh, yeah, that's nice. Yeah, but I think it needs to go the other way. No, you have to pull this. Or maybe I just sit somewhere else. Yeah, perfect. Thank you. Oh, well, anyway. So based on this logic, we could, of course, now draw many more samples from the GLM and visualize them if we have some MATLAB around. That's much easier. Now it's too dark. Just kidding. So again, so we just formulated the model and drew samples from it. We visualized the expectation parameter of the model, and we here visualize two samples that we drew from it. Yeah, it's very important that you don't confuse the line that is blue here with a line that you've seen fitted to data, because it's completely not that line. We will later also also add this line actually, but at present it's not there. Yeah, questions about what we did here in terms of sampling simple linear regression?
The 2, being on the 1, where, just as a data point, where is the 1 from the other side? So if you go a little bit to the left on the screen, it looks like that it would be 2 and then 2, 2. So on the x-axis, I would have thought it would have been 2 on the x-axis and then 2, 2 on the y-axis.
2 on the y-axis and 2, 2.
Or I just don't, I don't see the connection between 1 and 2.2, because they're...
Yeah, so the connection is, so the value of the independent random, not the independent random, but the independent variable, the first one is 1, yeah? Now 1, so this 1 here, gets mapped to the expected value of yy by means of this matrix product to the value 2, yeah? And now, so this is also then written up here again. And now a sample is drawn that is has its expected value at 2. So a very likely, based on the variance, a very likely value is, for example, 2.2. So this is why for the x value 1, which is this x value here, we sample something that is 2.2.
Okay.
Yeah, and this carries through. And this is actually, it's good that you brought that up, because that's you cannot that's fairly important. So that of course with a simple linear regression, you're somewhat constrained in what kind of data you can generate, because your expected value will always show this linear increase. So for example, different other models that you could formulate, of course, would have different offsets and different slopes. So for example, something like this, which has a different offset, or something like this, which also has a different offset and a completely different slope. So you can only generate, based on the GLM for simple linear regression, these kind of data patterns. But it's very important that the values that are defined in terms of the independent random variable you don't find them directly in the data. So it can be all over the place. And especially one thing that you can, of course, also do is, in this case, actually define the beta parameters to be zeros, and then sample each value, and then you would again just sample values around 0. So you can also basically create the case of no slope whatsoever, and just random noise if you want, based on this logic. Yeah, other questions? No. Good. So that actually concludes the model formulation now really for the moment. In the towards the end of the course, we will look at many more examples. So as promised, I will show you how ANOVA looks in the GLM, how multiple linear regression looks in the GLM, how ANCOVA looks in the GLM, how t-tests look in the GLM. We will do all of that. but specifically to understand also how t-tests come about, or how things like parameter estimation and getting basically fitting a line to data come about, we really need to now start talking about model estimation. Yeah, so we make a big cut here. So that's the big cut, and now start talking about model estimation. To this, the technique that we will talk about is maximum likelihood estimation. So the GLM, I'm using the GLM, of course, here as a tool to introduce you to the general logic of probabilistic models. Yeah, so the case that we now have defined Py, so the probability of y being a normal distribution of this type. This is important, or again, because now I'm already inconsistent like this. This is important for classical statistics and understanding fMRI data analysis and everything. But of course, you could also have a completely different distribution on this side as a model for some data. The logic, like what we've just seen, sampling simple linear regression, would be completely the same. Yeah. So you can think, for example, of applying nonlinear functions to this. So if somebody of you has seen logistic regression, which we will talk about in the summer term, you get that basically by applying some additional nonlinear function to this X beta. But you can also think that here this expectation parameter actually, so if you think again of a parameter, you can think that this actually results from the integration of some partial differential equations. Well, that's maybe not the best example because that would at least be two-dimensional. So let's say from ordinary differential equation. So there's a lot. So this is kind of a very general concept which I'm trying here to make very clear in terms of the GLM, and we've seen that now. What I've just said, so that basically you have some data and you that you want to model, and you specify a probability distribution for that. That's what I call a probabilistic model. And what, of course, which in our case takes this form, and what, of course, you want to do in terms of data analysis is that you want to think that data you observed was actually generated from such a probabilistic model. And based on this assumption, you want to now find the parameters that most likely, or most likely generated the data. Yeah. So just to say that in different words again. So in data analysis and using probabilistic models for data analysis, what we've done so far, formulating a model and then sampling it, that's nice and helps a lot in understanding the model. But it's not data analysis. It's a simulation that you do on a computer or in your head. For complex models, it can already be quite informative and interesting. Or, for example, if you apply another function based on some random general realizations, then you can study things like how random variables are transformed and so on. So it's all very interesting. And if you're a computational neuroscientist, you would be fully content in doing so and looking at the outcomes of your simulations and then write a paper. In cognitive neuroscience, we are interested in actually also obtaining data from the world using our sensors like the fMRI machine or the EEG machine, and then think and assume that these kind of data were generated by a probabilistic model such as this one. and then use this assumption to actually learn something about the parameters. Yeah? So this is one thing that is very important, and for your own thinking, I maybe at this point also introduce something that is fairly important, namely true but unknown parameters, which I will always refer to, true but unknown parameters. Because you can, this assumption that you use this, that you use a model to embed your assumptions about how data was generated, of course, only works, like I showed you before, if you assume that there are some parameters that gave rise to observed data, like we did when we sampled the simple linear regression, but you don't know them. And in fact, and when we now work through model estimation, you will never know them. Yeah. So with statistical modeling and probabilistic models, you never disclose the true but unknown parameters. But what you will obtain, of course, and this is what we will talk about at length now, is that you obtain estimates and estimators for these true but unknown parameters. Yeah, the true but unknown parameters you can in simulation, and like we did in our heads above, you can define and think what then happens. In data analysis, you will never you will never disclose them. You will never learn about them. Yeah. But this, so just as a first representation of that, I think we will or first discussion of that, I think we will come back to the notion of true but unknown parameters on many cases, and also dissociate clearly between them. Now, as for model estimation, I see actually that my time is running out, so I rather discuss some more general points here than we get started. In terms of model estimation, so estimating the parameters and evaluating the probability of data under a model, there is not one technique. Yeah, so model estimation, as we also discussed already in the introduction, comes in different forms. The first thing that is quite good to dissociate is what kind of estimates for the true but unknown parameters one wants to get. So what is the aim? Do you want a point estimate? Or do you want, which doesn't really have a name, do you want a posterior distribution if you want? I think that's the closest what that one can say, posterior distribution. And we will do the whole thing with regards to point estimates here. So point estimates can be obtained using maximum likelihood estimation, which will be our next big topic. Point estimates can also be obtained in terms of maximum a posteriori estimates, where you basically use the expected value of the posterior distribution as a point estimate. So you do Bayesian inference, but you actually then the only thing that you use is a point estimate for the true but unknown value. To make this at this point already maybe a little bit more concrete, we will have to talk about the parameters of the GLM, which are of course our beta parameter vector and our sigma square. Now, if you assume that there is some true but unknown value for beta, and in this case our beta is just a scalar value, then you could have a beta true but unknown of, for example, 1. And you can estimate this with a point estimate, which will usually be denoted by a beta hat as, for example, 2. Yeah, so 2 would be a point estimate for a true but unknown value. Yeah.
Does that mean that you have a value but you don't know what it represents, or what's the unknown?
If you mean by, I would say you know what it represents because it represents a certain contribution in your model, but you don't know its value. So you don't know the value of the true but unknown parameter, and you want to estimate it either with a point estimate, which you can derive from maximum likelihood, for example, or using maximum a posteriori estimates, or you do completely ad hoc. So of course you can also say, okay, I always estimate all my beta parameters and all GLMs that I assume as 2. That's also an estimate. It's just very bad estimates in most of the cases. Not in all cases, because if your true but unknown value is actually 2 for whatever you have, then it's the perfect estimate. But in general, because maybe true but unknown values take different values, a constant point estimate is maybe not the best idea. In terms of, because I'm trying to tell you that there are multiple ways to do model estimation. In terms of posterior distributions, of course, a standard way to derive posterior distributions is just analytically by what you might call Bayes' theorem. No, not you might call, but you call Bayes' theorem, so that you derive analytically a posterior distribution. Other ways to do that are, and very popular ways to do that are sampling approaches that are usually called MC-MC, where you actually use what we just did in our heads, but you do it in a computer to actually sample the posterior distribution, and then you usually have to do some form of density estimation on what you did. And you can combine that with some model selection criteria that approximate the probability of the data. So something like BIG or AIC, if you have heard these things. If not, never mind. It's not really important. Just for people that have heard some of these, I'm just trying to describe the overall picture. And for the others, I tell you that there's more to what we do. Another way to derive posterior distributions in an approximative sense, of course, this is approximative. Another way that one can use is variational Bayes, which is my persönliches Steckenpferd. So pet peeve, I think is the term. So variational Bayes is also an approximate Bayesian technique to derive posterior distributions. So what I'm trying to say is, for model estimations, there are many different ways to actually derive parameter estimates. Once you have derived parameter estimates and procedures to evaluate these, you actually don't know whether these are good procedures. So although there are general procedures, specifically maximum likelihood here, which we will discuss in detail, not MAP, but maximum likelihood estimation, we'll discuss in detail, only because there's such a procedure that allows you to derive a way to obtain parameter estimates, it doesn't mean that the parameter estimators and the resulting estimates are actually good estimaters. One example, which we will also see, is, for example, that the maximum likely estimate for the variance parameter of the GLM is actually biased, and that this is not necessarily good, and especially for these more complex estimation techniques like MC-MC and variational Bayes that try to approximate Bayes' theorem, essentially. There's actually no guarantee that they are good. They are just procedures to derive estimators. With Bayes' theorem and MAP estimates, I think the situation is a little bit different. So they can be, I think they can be thought of as being optimal in a very specific sense. But of course, again, only in a very specific sense. So now I successfully spent 10 minutes talking about some general stuff that maybe not said much to some of you, because I just went over some in-depth things which you might not have the basis for. So, but this allows me to be able to talk for 45 minutes, so that this video also looks 45 minutes on YouTube. And now we can actually stop and continue with model estimation and maximum likelihood estimation next week. Yeah.